In this video, we will discuss a lot of geometry, actually, in space. We will start with quadric surfaces. Okay. What is a quadric surface? It is a surface which is described by the zeros of a polynomial of degree 2 in space. So, okay, a quadric surface is a, okay, I will describe it a little bit differently. First is a generalization of conic sections. Well, recall, conic sections were simply parabolas, hyperbolas, and ellipses in plane. So, if we generalize conic sections to space, we obtain quadric surfaces. Well, recall what parabola, hyperbola, or ellipse were in plane. They were actually polynomials of degree 2, well, like y is x squared, or y squared minus x squared is 1. Namely, they were roots of these polynomials. But of course, these polynomials were of two variables. Now, in quadric surfaces, we will have polynomials of three variables. So, okay, thus, a quadric surface is the set of all points x, y, z in R3 satisfying, okay, a certain polynomial of degree 2. Now, we did not define such polynomials in three variables, so I will write it down. It simply means that you have products of x, y, and z's multiplied by coefficients and then added, but these products will never contain more than two variables. So, it is like ax squared, by squared, cz squared. So these are the square terms. Then the product terms, dxy, exz, fyz. These are all multiplied by coefficients. And then you have the single terms, gx, hy, iz. And, of course, you can have a so G, H, okay. So plus H is 0. So if you have such a polynomial of degree 2 in three variables, then, okay, the set of points satisfying it is called a quadric surface. Now, of course, this is a very complicated looking thing, and it's not practical to deal with it that way. So I will simply say that dealing with them in general okay, as a whole is not practical, okay, and is not necessary. And of course is not easy. Namely, even in plane. Okay. Consider x squared plus xy plus y squared is 1. Now, if we did not have this middle term, we would know that this is a circle. Now, what happens if we have the product xy? Well, it becomes an ellipse, but it is not a standard ellipse sitting in a vertical position with respect to the axes, but it's a rotated ellipse. Okay. In fact, it is a rotated ellipse. Okay, namely it's of this form. Okay. So the same principle also works in R3. That is, if you have products of x, y, and z's, okay, I mean something like xy or xz or yz, they point out to rotations. Well, we will not discuss rotations. So we will simplify them so that we only have x squared, y squared, z squared, and then x, y, z. Well, again, the presence of x, y, or z terms alone, together with the squares, points out to a shift. Very simply, think about in plane, x squared plus y squared plus 2x plus 2y, okay, equal to something. Now, this is a circle, all right? But the center is shifted to 1, 1. You are familiar with those shifts of parabolas or circles or hyperbolas. Okay. And we will also not deal with them too much. Okay. So, since, okay, mixed products point out to rotations, okay, and presence of x, y, z terms points out to translations. Okay, translation is just moves it along x or y axis or somewhere else, but does not rotate it. Okay. Okay. We will not deal with them. In detail, or rather not at all in the rotation case, so we will not consider them in general. Okay. So what we will do in this section? We will discuss the graphs. So we want to sketch these things. This will be done best by examples. Okay. The question is sketch. Of course, in R3. Okay. Now, to sketch something in R3 is not usually as simple as sketching something in plane, in XY plane. So we make use of the following, if you want, technique to sketch them. Okay. Now, a remark at first. Okay. To sketch a surface in space, okay, we consider the intersections with planes parallel to the coordinate planes. Okay. Well, why do we do that? Okay, just imagine you have a surface, something like a hill in space, the surface of a hill. Now, you intersect it, say, with a horizontal plane. Inside of the hill is empty, just the surface. So if you have a surface, you intersect with a horizontal plane, you get a curve. And it's easy to sketch curves. Okay. The resulting curves are called level curves. Okay. This approach is used a lot in geography. You must have noticed in geography things like this. Okay, these are used in actually topography, but nevertheless, suppose you have, say, a hill like this, okay, and you want to show the heights, etc. So what do? Well, you cut it with a horizontal plane, and lots of them, okay, and you get some curves here. So here you have a curve, here you have a curve, etc. And you show it as follows. Okay. At the top, say you have a curve of this form. It need not be a circle, of course, depending on the hill. And then you show it like this, and so on. Of course, here, the inside part, this one, is the highest one. The others are lower and lower. Okay? So from here, for example, in topography, you observe that on this side, on the left side, the hill gets steep. It immediately falls. On the right side, it falls gradually. Okay? So if you want to climb this hill, you would prefer the right side, not the left side. Unless, of course, you are a mountain climber. Well, so these are called level curves. And after we get an idea about these level curves, we put them together in our minds, in R3, and then obtain the result. This will be very clear from the examples. Okay. Say our first example. Suppose we have this, but in R3. Obviously, this is a circle of radius 2 in plane. But it is not a curve in R3, it's a surface. So let us intersect this surface with some horizontal plane. So, intersecting this surface with, okay, a horizontal plane, or rather horizontal planes, we get the following. Now, this is the z-axis, okay. This is, say, the level z is 0, namely the standard x, y plane. Of course, all of these axes are perpendicular to each other, as we already considered. Now, when z is 0, what do we get? Well, we look at the equation. Of course, then we get x squared plus y squared is 4, because there's no z in it. Well, this tells us that indeed we have a circle here, okay, with radius 2 in this plane. Now, change that. We still get x squared plus y squared is 4. But this is a different level because z is greater. So we have something like this here. Okay. Z is bigger, we are elevated, but still we get the same figure. So we still get the same circle with radius 2. Now, when we consider a negative z, for instance, it doesn't depend on z, so it's always a circle with radius 2. Okay. It's always a circle with radius 2. Now, these curves are on the surface because they are intersections of the surface with the planes. Well, we then imagine the whole figure. It's always a circle like this, only we give it a level. So it goes up and down. Well, when we discuss this, okay, we obtain the following figure. Thus, okay, this is always the same circle of radius 2, centered, I did not figure the whole thing, so let me sketch it. Okay. So somewhere here you have your xy. Sorry, a better picture would be this. Okay. You have your x and y axes. This is the z-axis. You always have the same circle throughout. Okay, if you imagine the totality of all these circles going up and down, you clearly obtain a cylinder. But this is not the standard elementary cylinder in high school geometry because it's not bounded. So it goes up and down. So it is an unbounded in z direction, cylinder. So this is a cylinder equation in space. It's the surface of a cylinder, but it's an infinite cylinder. As a similar example, again a quadric surface, let us consider, say, z is x squared. Now, what does this look like? Well, this is a case where we don't have the y variable. So whatever y is, we always get the same parabola. Okay, that means if we give different values to y, geometrically, intersect this surface with y equal to constant plane. So, considering intersections with y equal to constant surfaces, of course, these the planes actually, I mean, they are surfaces, but they are in particular planes, okay, we obtain. Now, what is y equal to constant plane? Well, that is just like the zx plane, where y is 0, but moved parallel along the y-axis. So it looks like this. This is x, and this is y. Now, if you consider, say, a fixed y value here, actually here, okay? This would be y equal to some y1 plane, okay? It is vertical, it's parallel to the zx plane. It's just moved a little bit in this direction. On this plane, okay, when y is y1, we have z equal to x squared. Well, this is the z-axis, this is the x-axis. So on here, it looks like this. It's a parabola, z is x squared. Now move it to some place here. Okay. This is, say, y is some y2 bigger than y1. Well, we again get the same parabola. It's still z is x squared. Okay, note that the x-coordinate and the z-coordinate, even though shifted, okay, the lengths, etc., remain the same. Only y changes. So, whatever we do, of course, we can do the same thing for some y, which is negative. Okay. Then we would have, again, such a plane. Okay. So we would again obtain the same parabola. Okay? This is, remember, the x-axis. This is the z-axis. So this is the parabola. Z is x squared. Again, what happens is we have a parabola, okay, and it's moved along the y-axis. So in our imagination, if we put them together, okay, obviously we will get something like this. Okay. But this is the surface, because these are the parabolas. Okay. It is like a trough where horses drink water, okay? But again, it is an unbounded one. Namely, okay, this does not stop here. It continues in both directions up to infinity. Okay. Okay. Now, this quadric surface, where one of the variables is missing, is always called a cylinder. Okay. Meaning that, okay, a variable does not appear in the formula. Okay. So there's a simple way of sketching these surfaces. You sketch one of them, but you are careful about the missing coordinate. So along the missing coordinate, you draw one of them, a parabola in this case, and then you just move it back and forth along y in this case. Okay, previously we did that for the z direction, obtained a more regular cylinder. Here we obtain something like this. Of course, the sides again are not bounded. They also increase up to infinity. So it's an infinite parabola on both sides and you slide it along. Okay. As a second example, let us now sketch z is x squared plus y squared. Now this is different from the cylinders because we have all of them, x, y, and z, present in the picture. Now we can, of course, intersect the unknown surface with various planes parallel to the coordinate planes. But usually, not always, the easiest one is what we did so far in the first example, namely that we intersect it with horizontal planes. So intersect with horizontal planes. Okay, this means that we are working on the z-axis. So let us start, say, with the z equal to 0 starting point. When z is 0, that is on the xy, this is x, say this is y, on the standard xy plane, we clearly see that x squared plus y squared becomes 0. Well, this is possible only if we have exactly one point. So just the point 0, 0. Namely, this is a single point here. From the equation, it is obvious that z negative cannot be true, because the right-hand side is non-negative all the time. But z can be bigger. So suppose we have a slightly bigger z value. Say z is positive now. Then we have x squared plus y squared is root z squared. Well, throughout this plane, z is constant. It is equal to some positive value. But then we obtain, obviously, a circle. So this is a circle now, here, at this level. The radius is square root of z. Now let us make our z even bigger. Okay. So we observe that as, let me say z1 here, for simplicity. So say z2 is even bigger than z1. Then we will have a larger circle, okay, with radius root z2. What happens is that when we go up, that is, if we have a higher altitude and we look at a horizontal cross-section, we always have a circle, but these circles get bigger and bigger. So when we put them together, okay, we obtain something like this. For example, let us connect these points where, okay, we are on the y-axis. These are supposed to be parallel here. And let us connect these points. Clearly, these points get away from the z-axis, so maybe they will go like that. On the other side, the same happens here. Okay. Now, the picture will look like, of course, this. You always have circles getting bigger and bigger, but how do they get bigger? Namely, what are these curves? So, okay, we want to determine the curve gamma. Okay, what is gamma, by the way, when we look at the curve gamma, that is these points, okay, this point is on the level Z2, it is on the circle, of course, but at the same time, it's on the y-axis, which means, okay, x is 0. So, because this is the y-axis, okay, and this is the y-axis, the intersections are on the z y plane, and therefore, okay, the value of x must be 0. So on gamma, okay, the points are intersections of intersections with the zy plane. So x is 0. Now what happens if x is 0? So z is 0 squared plus y squared. So on the zy plane, okay, the picture is always a parabola. So I deliberately drew strange curves here, but it is a parabola all the time. Hence, okay, we conclude that we get, okay, here we have a single point at the bottom, and on the side we have a parabola, and here we have circles all the time. And because we are dealing with a surface, the inside is empty. There is nothing inside, so we get this. It is called not a parabola, as in the conic section case. It's called a paraboloid. Here, of course, this is the z-axis, okay? And for every circle, you have your x and y's. So it's an increasing circles as we go up, putting together everything, and knowing that the side is a parabola, okay, we can get a rather precise picture. Okay. Another quadric surface is, say, x squared plus y squared minus z squared is 1. Now, we will do the same thing here. So I will go a little bit faster in this example. So I will intersect the picture with z equal to 0 at first. Well, when z is 0, clearly we get x squared plus y squared is 1. So we have a circle of radius 1 over here. Now, let us make z a little bit bigger. Then, of course, if z is a little bit bigger, we get x squared plus y squared is 1 plus z squared. But z is a positive number now. So 1 plus z squared is bigger than 1. This says that z is constant at this level. Okay, z is positive, okay, but constant. Okay. So let me say, since z is constant on this plane, okay, well, you can say z is, say, z1, okay, we get circles. Again, but, of course, z1 is positive, so the radius is bigger than 1. So, this time we get, okay, a larger circle with radius root 1 plus z1 squared, whatever. It is obvious now that when we make Z even bigger, we will get even larger circles. But because we have a square here, it doesn't matter if Z is negative. If Z is negative, its square will be the same as the positive term squared. And so at the bottom also, we have such circles getting bigger and bigger all the time. Okay. Now again, it is not clear what this looks like because okay, we only know that we start with a smallest circle, and when we go up, the circles get bigger. When we go down, they become bigger again in a symmetric way. Now, to obtain what exactly is happening, this time, say we put together, okay, these points, where, okay, we are looking at the zx plane. Remember, these were x's. And here, of course, we would have a similar thing. We would be considering a larger value. So what happens is we have a curve like this. On the other side, a similar thing happens. And so on. Well, this is, of course, not a good picture. So actually, it would be a larger value. So it would look like something like this. So maybe something like this. So the radii get larger, all right, but how? That is the point. Well, clearly, the curve gamma is the intersection on both sides of the vertical plane zx with the surface. So gamma is the intersection of xz plane with the unknown surface. Okay, but xz plane means y is 0. So, okay, we get from the original equation, okay, I just erased it. It was x squared, okay, plus y squared, which is 0, minus z squared is 1. Now, in the zx plane, okay, this tells us that x squared is 1 plus z squared, so z cannot be x cannot be smaller than 1 in the first place. Okay? And we recognize this as the equation of a standard hyperbola. Okay. Because x cannot be smaller than 1, it looks like this. So, putting them together, okay, we get a hyperbola, and the horizontal sections are circles. So, it is like this. Of course, again, it goes to infinities. It is not a finite bounded figure. Okay, it goes to infinities, but it is a rotated thing. I will comment about this later. Normally, just looking at such a gamma alone would not suffice, but for quadrics, if you have x squared plus y squared term, it will be sufficient. I will comment on it later. This is called a hyperboloid. Okay. Because the surface consists of one surface, this will be meaningful in the next example. It's called hyperboloid of one sheet. Right. Now let us modify our example a little bit. Say this time we have x squared plus y squared minus z squared is minus 1. Now, what difference does this make? Again, we do the same thing, okay? Consider, okay, level curves, okay? That is, intersections with z equal to constant planes. What do we get then? Well, let me draw a very long z-axis and say z is 0. Okay. Obviously, it's not possible. When z is 0, x squared plus y squared is minus 1. Not possible. So there is no point on z equal to 0 level. But we can easily generalize this. Okay, write this as, let me put it here, x squared plus y squared is z squared, and we have 1 on this side. So this tells us that z cannot be smaller than 1. It is 1 plus a positive number, so z squared is bigger than 1 all the time. Well, this means, because we have square, z cannot be between minus 1 and 1 open interval. So the smallest values z can take is 1. When z is 1, clearly we have a single point because we have this. On the other hand, similarly, when z is minus 1, the same thing happens. So we have a single point here. We have nothing in between because z is not in absolute value less than 1. Now let us elevate this a little bit. So if z is bigger than 1, then of course as z gets larger and larger, clearly we get x squared plus y squared, okay, z squared minus 1. Now this is a strictly positive number and the radius is positive, so we get a circle. So here, okay, we get some circle. Again, clearly, when z value gets bigger and bigger, okay, the radius gets bigger, so at higher levels, we have larger circles. But the same is true down here. So we get circles and then larger circles. So, as in the previous case, okay, we have circles starting with level z equal to 1 from a single point and increasing in radius above, or starting with minus 1, and when we go down, they get larger and larger circles. Well, by the same approach we had a minute ago, okay, let us say connect these points together. Okay. And also on this side, and also here, like this, so here, and so on. Okay. These curves, call it gamma curve, okay? Again, gamma is the intersection of the surface with, okay, the z-x plane. Well, which is y is 0. So the equation becomes, when y is 0, we get x squared minus z squared is minus 1, or is minus 1, okay, or z squared minus x squared is 1. Now, this is x, this is z, and the z values cannot be smaller than 1 because z squared is 1 plus x squared, in absolute value, that is. So, okay, this is a hyperbola. Where this time we have this formulation. Okay. Well, putting these points together, so we get, okay, at the top, this hyperbola, at the bottom, the other branch, and of course we have circles here. Throughout. Okay. The radii get larger. Okay. This is the level z is 0. We have nothing there. Here we have 1. Here we have minus 1 for z. Of course, this is the surface in question. Again, it continues to infinities, and because it's determined by a hyperbola, it's called, again, a hyperboloid, but of two sheets, because we have two of them. Okay. Well, that would be my 3, so 4. Well, we can similarly generalize an ellipse. Well, what was an ellipse after all? It was x squared plus a squared plus y squared over b squared equal to 1 in plane. Okay, a, b are positive numbers. Now, in space, we can, of course, add another term, and this becomes a generalization of the ellipse. What does it look like? I will not go into details here. We got the idea, more or less, okay? This tells us that the largest value of x can be a. Because if x is bigger than a, everything is positive, and this would be bigger than 1, so the equation is not satisfied. So x can be a or minus a because of the square. Okay? So we have here, okay, a, and here minus a as the largest possible values of x. Well, for y, the same thing happens with b's, and they need not be the same, of course. And for getting z, that is putting z equal to 0, on the xy plane, we get a nice ellipse. But at the same time, we can elevate it a little bit. When we elevate it, that means if we give a positive z value, a little bit bigger than 0, then, okay, clearly all these points can go up, but x cannot be a anymore. It has to be smaller, otherwise the equation would not be satisfied. So, similarly then, we have c's here and minus c, and we have ellipses on this side as well. Okay. Because A, B, C can be all different, okay, like maybe a ball in American football, or a very regular sized egg, okay, could be termed as an ellipsoid. Okay. It's a generalization of the ellipse directly this way. Well, a quite worthwhile example, that is my fifth example here, is the following. Now this is interesting in many respects, and it's a nice thing. So let us work on it a little bit. Let us do the same thing, that is, intersect our surface with level surfaces, z equal to constant surfaces. So when z is 0, okay, clearly we have a single point. When z gets larger, okay, somewhere here at this level, okay, we have a circle. The argument is the same. The circles get larger, and because of square, they are symmetric, and at the bottom they get larger as well. So the whole thing, as in the hyperboloid cases, is in determining what happens, okay, at these points. Well, that should be parallel somewhere here, and so on. So if this is the curve gamma, we have the symmetric version, of course, on the other side, and so on, okay? Calling this gamma. Gamma is the intersection of the surface with the plane z, okay, this was the x-axis, so with the zx plane. That means y is 0. So we have z squared is x squared. Which means, of course, z is x or z is minus x. But in the zx plane, these are just straight lines. So putting them together, of course, this figure suggests that when you combine these circles together, you have a surface of this form, and of course it is the well-known surface. If these are straight lines, it's a cone. Okay. All horizontal cross-sections are circles. It's called a cone. But note that this cone is again unlike the elementary geometric cone, okay, where we considered only one part of it, not both. Okay, we had a tip and a base. Here we don't have a base because these sides go to infinity. And we have both parts together. This is the cone in geometry which generates the conic sections. Just, I will not go into details here, but just think of the following. In this cone, okay, suppose you cut it by a vertical plane parallel to the z-axis. Okay? What do you get? You get a curve at the top, you get a curve at the bottom. It's called a hyperbola. Okay. Intersect it with a plane parallel to one side, something like this. Okay? The curve you get is called a parabola. Intersected with a more horizontal looking plane, you get something like this, which is not a circle anymore, it's an ellipse. That's why they are called conic sections. A last remark about these sketches. If in the expression of a conic section of a quadric surface, let me say, a quadric surface, okay, one only has, okay, x squared plus y squared term, then it means that z depends on, okay, not x or y, but it depends on the distance squared from the z-axis. Okay, the distance from the z-axis is root x squared plus y squared. So, okay, it means that at any point where x squared plus y squared is constant, the z values are the same. In other words, on circles, the z values are the same. So the surface is obtained by a rotation. Okay. Then the surface is obtained by rotating, okay, a curve. Okay. For instance, in the case of a cone, take a straight line through the origin and rotate it around the z-axis. Okay, let me say about z-axis. Or in the case of a paraboloid, z is x squared plus y squared, and you have a parabola, and you rotate the parabola around the z-axis, you get a paraboloid. Similarly, for the hyperboloids. So this is a useful knowledge. Of course, one can change the roles, namely, if you have only x squared plus z squared term, it means that you have a rotation about the y-axis this time. So these modifications are certainly meaningful. Thus, for example, suppose we have e to the minus x squared plus y squared. Okay. Now this is very difficult to sketch if you start from nothing. But it's a function of x squared plus y squared, so it's a rotated figure. So let us look at what we have, okay, for a level z, or rather say y is 0 for some point. Well, in the zx plane, so let me say if y is 0, so on zx plane, we get, okay, precisely this. Z is e to the minus x squared. Okay. You may remember from Math 119 that this is a picture like this. Okay. That is this one. Okay. Well, when x is 0, you have 1 here at the top. So it is this one. Now rotate this. Okay? So rotate about z-axis. Okay. What do you get in that case? Well, you get, it's difficult to sketch it perhaps when you rotate that, but it's like a hilltop, like this, okay? But rotate it, and so on. But it's all over the place. Okay. Or maybe I should do it as follows. Okay. It's a rotated form, but it's all over the place. Okay. Or say z is logarithm x squared plus y squared. Again, it's a rotated surface, so you only have to rotate z is logarithm x squared, which, of course, okay, is 2 times logarithm x, if x is positive. So you get this. If x is negative, you have symmetry. You rotate that, and you get such a figure, where one side is the logarithm function.